Hey everybody, today we're going to do problems 11 through 15 on worksheet number 4. Alright, let's get started. How many grams of water are formed when 12.5 grams of hydrogen reacts with excess oxygen? Well, clearly what we have to do is create our balanced chemical equation, which is hydrogen plus oxygen gives us water. Now, of course, we have to remember that hydrogen and oxygen are Brinkelhoff elements. And to balance this, we need to have two waters over here, which means we need two hydrogens over there. So we're now balanced. And we have 12.5 grams of hydrogen. We have excess oxygen, so we don't have to worry about that. And the question is, how much water do we come up with in grams? Okay, so let's start with the information that we're given, which is 12.5 grams of hydrogen gas. And what we're going to have to do is we have to go from grams of hydrogen to moles of hydrogen. From that we have to go to moles of oxygen, moles of water. And then we have to go to grams of water. Let's go ahead and do that. We start with grams of hydrogen. We go to moles of hydrogen. And from moles of hydrogen, we go to moles of water. That's our target. And from moles of water, we have to go to grams of water because that's what we're asked for in the problem. Okay, it asks us for grams of water at the end. Okay, so 1 mole of hydrogen, we have to figure out what that weighs. We pull out our trusty periodic table, multiply 1.0079 times 2, and get 2.0158. Now, we then look at our coefficients in front of hydrogen and our coefficient in front of water. And they're 2 and 2, so they're going to cancel each other out. That one's simple. And 1 mole of water by now, you should know that weighs 18.015 grams. Okay, we do our math. And when we do all of our math, we come up with 112 grams of water. And we have 3 sig figs in our problem, so we have 3 sig figs in our answer. Okay, that's it for number 11. Number 12. Now, the first thing we better do is balance this equation. Alright, so I see over here on the left, I see 2 sodiums, so I have to have 2 sodiums on the right, which means I have to have 2 chlorines on the left. I have 2 hydrogens now on both sides, that's good. I have 1 carbon on both sides and 3 oxygens on both sides, so I am now balanced. Okay. How many liters of carbon dioxide? So that's what my target is, liters of carbon dioxide. So it's asking for these in liters are formed when we have 12.3 grams of sodium carbonate. Well, that's this one. 12.3 grams of sodium carbonate and 2.0 liters of hydrochloric acid. All right, so this means I have to do a stoichiometry problem, and I have to do it twice. So let's go ahead and do that. 12.3 grams of sodium carbonate. And we're going to liters of carbon dioxide. So I have to go from grams of sodium carbonate to moles of sodium carbonate. And then from moles of sodium carbonate, I have to go to moles of carbon dioxide. And then from moles of carbon dioxide, I have to go to liters of carbon dioxide. And that'll give me an answer. All right, well, I know that 1 mole of sodium carbonate, I have to go look that up on the periodic table, add everything up, and that should be 105.988 grams. And I have 1 of these and 1 of these, according to my balanced equation up the top. And 1 mole of carbon dioxide is 22.4 liters. So when I do the math there, I come up with 2.60 liters. 3 sig figs in my problem, 3 sig figs in my answer. All right, let's try my other one, which is 2.0 liters of hydrochloric acid. And let's go from liters of hydrochloric acid to moles of hydrochloric acid. And then from moles of hydrochloric acid to moles of CO2. And then for moles of CO2, this is going to look real obvious because it's the same as the thing above it, liters of CO2. All right, so 1 mole of CO2 is 22.4 liters. And I have 2 moles of HCl up the top and 1 mole of carbon dioxide. And every mole of carbon dioxide is 22.4 liters. So this is real easy for me to do because my 22.4's cancel, so it's 2.0 over 2, which is 1.0 liters. Only 2 sig figs in this one, 1.0 liters. So clearly, this is my limiting reactant. My hydrochloric acid is limiting. The maximum I can produce is 1.0 liters of carbon dioxide gas. Okay, number 13. How many grams of precipitate are formed when 24.3 grams of zinc nitrate reacts with sodium phosphate, which means this is a double replacement reaction, so it's going to be zinc phosphate plus sodium nitrate. And let me balance my charges. Zinc nitrate, that means I've got 2 nitrates because it's a +2 and a -1. This is a -1 and a +1 and a -3, so when I crisscross them, I get Na3PO4. Zinc has a 2 charge, phosphate a 3 charge, so I have to have 3 of those and 2 of those. And sodium and nitrate are +1, -1. So now I have to go and balance my charges. Let's see, I have to have 3 sodium, so I put a 3 over here, but I have to have only 2 nitrates, so that's not going to work, so I'm going to have to put a 6 over here to make this whole thing balance. Alright, so if I have to have a 6 there, then, let's see, I need 6 nitrates, so 6 of those, I need 3 of those, I need 3 zincs, I need phosphates, I need 2 phosphates, I have 2 phosphates, 6, yep, I'm all balanced. Okay. So, how many grams of precipitate? Well, wait a minute, we've got to figure out what a precipitate is. Well, you need to look at your solubility chart. Yep, you pull all this stuff together, and you'll notice that everything with nitrate is always aqueous. Everything with sodium is always aqueous. Everything with sodium and nitrate is always aqueous. So this must be our solid. And if you look at your solubility chart, you'll find that that's true. Alright, so this is the one we're trying to get to. And we're starting with 24.3 grams of zinc nitrate and 20.5 grams of sodium phosphate. So I'm going to go and do a double, I'm going to do 2 stoichiometry problems. 24.3 grams of zinc nitrate. And that's my first one. And my other one's going to be 20.5 grams of sodium phosphate. Okay, let's do this one first. We go from grams of zinc nitrate to moles of zinc nitrate. And we go from moles of zinc nitrate to moles of our target. And in our case, the moles is moles of our target, which is the precipitate, which is zinc, PO4, 2. And because it's asking us for grams of precipitate, we have to go one more step from moles of zinc nitrate, moles of zinc phosphate, I'm sorry, PO4, 2 grams of zinc phosphate. Okay, so now we have to do, obviously we have to look up a bunch of stuff on the periodic table here. So we find out that zinc nitrate weighs 189.398 grams. And our zinc nitrate has a 3 in front of it, and we're going to something with a 1 in front of it. So a 3 and a 1. And 1 mole of zinc phosphate weighs 386.11 grams. Okay, when we multiply that out, that gives us 16.5 grams of zinc 3 phosphate. Zinc phosphate. Okay, so now let's do the same thing down here. We have to get rid of grams of sodium phosphate. Yeah, these do take a while, don't they? And then we go from moles of sodium phosphate to moles of zinc phosphate. Now from here on out, it's going to be exactly like what we see up above us. And we go from moles of zinc phosphate to grams of zinc phosphate. It's 386.11. All right, so we have to go out to do our thing with periodic table, figure out our molar mass of sodium phosphate, which is 163.94. And let's see, sodium phosphate has a 2 in front of it, and zinc phosphate has a 1 in front of it, and we already filled in the rest. If we do our math here, we get 24.1 grams. So clearly this is how much we can possibly make. So that tells us that this was limiting up here, which was our zinc nitrate. Okay, so the maximum that we can make is 16.5 grams of zinc phosphate. Okay, let's go on to number 14. We have 3.25 grams of potassium chlorate, that's KClO3, and it decomposes into potassium chloride and oxygen gas. All of our charges are balanced, so we have to put in some coefficients to balance our equation. And now let's see, we start with 3.25 grams of this, and we're decomposing, and it's asking us for liters of oxygen gas. So we have to go from KClO3 to oxygen. Stoichiometry problem. 3.25 grams of KClO3. And we have to convert from grams of KClO3. Right, had a slight problem there. All right, let's continue. We have 3.25 grams of potassium chlorate, so we have to get rid of grams of potassium chlorate down in the bottom here. And we have to go to moles of potassium chlorate up here. And we have to get rid of moles of potassium chlorate and go to moles of, well, our target over here is oxygen, so we have to go to moles of oxygen. We have to get rid of moles of oxygen, and our question asked us for liters of oxygen. So we specifically have to go to liters of oxygen. And now we fill in some numbers. 1 mole of KClO3, we have to figure out how much what its mass is, and that's 122.548 grams. And our KClO3 has a 2 in front of it, our oxygen has a 3 in front of it, so that's a 2 to 3 ratio. 2 to 3 ratio. And our liters are 22.4. So when we multiply this out, we get 0.891 liters. 3 sig figs in our problem, 3 sig figs in our answer, and that's that one. All right, last one for this podcast is number 15. We have sodium chloride. We all know what sodium chloride is. That's table salt. Sodium chloride reacting with excess silver nitrate. Excess meaning we have more than we need, so that's good to know. Gives us 3.45 grams of a precipitate. Well, this is a double replacement reaction, so it's NaNO3 plus AgCl. Right, well, let's see. Let's balance our equation first. And everything is balanced. And our charges are balanced because everything is plus 1 minus 1. Let's look at sodium chloride. That is definitely aqueous because it includes sodium. And anything that includes nitrate is also aqueous. So over here, sodium and nitrate must be aqueous, which leaves us silver chloride, which is what our solid is. Again, you can look that up on your solubility table to make sure you know that. We start with 2.25 grams of sodium chloride. We have this in excess, so we don't have to worry about it. And we're trying to figure out how much precipitate is formed. All right. So, and that's obviously going to be in grams because we are going to be figuring out our percent yield based on grams. Let's go do the problem. Normal stoichiometry problem. So we're going from grams of NaCl. What do we have to go to every time? Of course, we go from grams of NaCl to moles of NaCl. And from moles of NaCl, we go to moles of silver chloride because silver chloride is our target. It is the one that's a precipitate. We go from moles of silver chloride to grams of silver chloride. So we have to figure out how much sodium chloride weighs, and that's 22.99 plus 35.453. So that is 58.443 grams in 1 mole. And we have 1 and 1 because our ratios are all 1 to 1. And our silver chloride, that's a heavier one. That's 143.32 grams. This is going to give us 5.52 grams of AgCl, silver chloride. However, what we actually got was 3.45. And if we remember, the way we do percent yield is we take what we actually got, we divide it by what we expected to get, which is 5.52 grams. We multiply by 100%, and that gives us our answer, which is going to be 62.5%. 3 sig figs on top, 3 sig figs on the bottom, 3 sig figs in our answer. All right, folks, that's it for that podcast. Questions? Please see us in class. We'll be happy to help you. Have a great day. Take care. Bye-bye.